Welcome back. So we are in the middle of working out the details of the two-body problem, two mutually gravitating objects in an otherwise vacuum. In the previous video, we set up the problem. We expressed everything in center of mass coordinates such that our position and velocity coordinates are now just the relative r and v, relative position and velocity vectors. And we sort of bit off part of the problem by looking at the Euler-Lagrange equation in the theta coordinate in the plane in which the particles move. That gave us angular momentum conservation and Kepler's second law. Now we can do the rest of it. So we looked at angular momentum conservation. Why not look at energy conservation? That ends up giving us a nice differential equation. If we specify the total energy E here and the angular momentum L, what we sort of have is a quantity that's a constant, essentially E equals, these things here. And two of the three terms just involve functions of R. The other one just involves R dot, dr dt. And when we do that, we can solve for that dr dt in terms of just a function of R, and that will give us a nice separable differential equation. When we do that, one of the things that is traditional to do is to take the potential energy term and this other term that eventually, that we saw grow out of the R theta dot component of the velocity. But since it involves angular momentum conservation, this is often called a centrifugal potential. And together with the gravitational potential, it's an effective potential. It's an interesting non-monotonic function that we'll look at soon. But yeah, so we have dr dt equals just a function of R. So we can rearrange it a bit. It's separable. Integrate the R parts to get a function of R, integrate the dt just to get t itself. That gives us t as a function of R. Well, mathematically, then you can just take that and invert it to get R as a function of t. Now, it's sometimes not as easy as it sounds because, in our current days of computers, we traditionally think of these things, if we have a function of t of R, it's just, a column of t numbers and then a corresponding column of R numbers. Inverting it just means sort of switching the orders or switching the axes if you plot them. Mathematically, it can be a more involved thing. So now if we actually can do that, if we know R is a function of t, we can go back to the conserved quantities. Now look at the angular momentum conservation. If we know L, we now know R and M as of, R is a function of t. What's left is d theta dt, and we can integrate that for theta of t. We can integrate that to get, so we now know R of t and theta of t. That's the actual complete description of the trajectory of this one pseudo particle that we can change coordinates and go back to R1, R2, V1, V2, and all that. But now, as I've described it, the most general way of doing that is not amenable to nice analytic functions. So in general, it needs to be done numerically. So we'll come back to that. We'll discuss it in a little bit in the next video. But what I wanted to do here is, as I said on the first slide, bite off another piece of this so that we can get some additional insight about what these systems are doing. And to do that, we need to start plugging in values for the potential energy. We know what it's going to look like. We've derived it, right? It's just minus g m1 m2 over r, and that g m1 m2 is often written as just a constant. Physicists tend to call that gamma. So yeah, gravity is one of the commonly seen forms for a potential energy. Bertrand in the 1800s showed that if you want to search for orbits r of t that are closed orbits, in other words, when you take theta all the way around from 0 to 2 pi, that the r comes back to exactly where it started. there actually are only two forms of the potential energy that allow that. One is gravity, the other is the simple harmonic oscillator potential that you've seen in physics classes. So closed orbits are a possibility when we're using gravity. Oh, and of course, what do we want to do? How do we want to move forward with this? Of course, the thing to do, we've already looked at the Euler-Lagrange equation for the theta coordinate. Now let's do it for the r coordinate, because this will actually give us a way of looking at the shapes of the orbits. I talked about solving for r of t and theta of t. That's nice. It's nice and complete. But if you combine those together to form the function of r of theta, that's an actual shape that you can plot on your polar coordinate graph paper or whatever to see what the orbit actually looks like. So, and I'll show you how we get there. So we've got our Euler-Lagrange equation for r. We can do those derivatives of the Lagrangian. We've already written E, the total energy, as kinetic plus potential. Lagrangian is just kinetic minus potential. So we can write those in the same way, do the derivatives. There are two different terms with r dependence. So there's going to be two terms for the partial derivative with respect to r, one term with respect to r dot, that's just the acceleration. And we can rearrange things a bit. And this really is just F equals ma, Newton's second law, again, as we've seen. But it's just now written in the particular coordinate system that we've chosen. This nice polar coordinates in the plane that's perpendicular to the angular momentum vector. So we've got the force, the force on the system, which is just minus the gradient of the potential energy, and then an acceleration-like term on the left. If I'm sure you've written out, velocities and accelerations in different coordinate systems, and it's got these multiple terms in it, and we can take this extra term in the acceleration and rewrite it a bit. If there's a theta dot, we can make use of the angular momentum conservation. This force, we can also divide it by the reduced mass of the system to get an acceleration, and rewrite different terms for how to actually solve for r of t or t of r, depending on how you do it. So you could actually follow this chain of equations to get that same solution for t of r, and then r of t, and then everything else. But there's going to be a slightly different way that we're going to look at this. So we do have this equation, but there is a change of variables that we can implement by just looking at a new variable that we define as 1 over r. I think the first person to do this was named Binet, and we'll see that this equation of motion becomes something called Binet's equation. But it'll eventually give us a way of writing a differential equation for the shape rather than the time trajectory of the particle, which is what we have up here. Well, we can do that. We can actually, by taking some derivatives of this new variable with respect to theta, we can work out the math of what those derivatives look like. And it turns out that we eliminate time as the dependent variable and turn it into a theta. So you can see how we do it here. If we take du d theta, we can use the chain rule to work it out. Du dr times dr d theta. U is just a known function of r, so we can take the derivative of that to get du dr. Dr d theta, well, again, this is something that the mathematicians might not like when we do, but this is a small differential over another small differential. But since we already have all these equations in terms of the time variability, why don't we just divide each of these differential things in the numerator and the denominator by a dt, so that this numerator thing becomes an r dot, the denominator is a theta dot, and guess what? Whenever we see a theta dot, we can use angular momentum conservation to write that in terms of the nice constant L and other functions of R. Turns out this helps to eliminate some of the extra functions of R. So now if we solve this for R dot, we've now got the time variability of R as a function of a theta derivative of this new quantity. And you could do that again for the second derivative. And doing that gets rid of all the dots, gets rid of all the time derivatives, and turns them into theta derivatives. So this down here is Benet's equation. It's a second order differential equation for the quantity u as a function of theta, and u is just r. So this gives us an equation for the shape of the orbit, which is nice. Okay, well, Benet's equation is written like that. And, you know, treating it as a differential equation, you know, if we know the force, we can plug in for that right-hand side and then integrate 2 times to get a u of theta. That's what we're going to do, and I'll show you how to do that in a minute. But one of the reasons people were fascinated by Benet's equation in the 1800s was that there's another way of getting at solutions, and that is if you know the shape of an orbit, you know, u of theta, you can work out the left-hand side as just a function and solve for the force. So essentially, if you're, you know, looking out in space and you're seeing, say, the orbit of Mercury, which is elliptical, but it deviates a little bit from an exact ellipse. If you have exact measurements of that shape as a function of theta, you can plug that in here and figure out what are the perturbing forces on Mercury that are causing it to deviate from an exact ellipse. So yeah, there was all sorts of problems that could be solved by this sort of backwards approach to Benet's equation, which is interesting. Right, but let's do it in the forward approach. Let's just solve it as a differential equation, right? We can write the force by, you know, taking our classical gravitational potential and taking the, you know, minus du dr gradient of it, and then writing it in terms of this new variable u. U is just 1 over r. And the nice thing about it is that on the right-hand side of Benet's equation, it's the force divided by u squared. But if the force contains a factor of u squared, everything else is a constant. So the right-hand side of Benet's equation is a constant for nice Newtonian gravitational potential. And that is a nice, helpful thing for solving it because, right, if it was some weird function of u, that would complicate the whole differential equation solving aspect of it. But if it's a constant, all we need to do is to create one more new variable, but it's a straightforward new variable. It's just this new variable that we call y. It's just u plus a constant. And it's that same constant that appears on the right-hand side of Benet's equation. And it's got a negative sign. Yeah, I'm not sure whether it's actually negative on the right-hand side or not, but when you plug this in, it gets rid of it, right? So the new version of Benet's equation is just second-order derivative with respect to theta plus the thing itself equals 0. That's just the simple harmonic oscillator equation, right? The solution to that, y as a function of theta, is just a sine or a cosine. Beautiful. But we're now several steps removed from r as a function of theta. So, well, first we can solve for y as a function of theta. You know, you could either write it as a constant times a sine plus a constant times a cosine, or you can write it like I did here with just a single cosine, but still 2 free parameters that tell us the offset, the phase and the amplitude of this sinusoidal function. And then we can go from y back to u, from u back to r, and now we have r as a function of theta. This is the actual shape of the orbit that you can plot in polar coordinates. And when you look at how these look, and I'll talk more about how I've renamed some of the constants here in a second, but this is now a conic section. And you've seen these, but this is just basically geometry of circles, ellipses, parabolas, and hyperbolas with one focus at the origin of our coordinate system, which is the center of mass. Yes, okay. So right, I just wanted to talk more about these constants for a second. The constant E, the eccentricity of the orbit that I put here is really just a renaming of the y0 amplitude of the sinusoid that we had to specify for the initial solution for y. E turns out to be a more natural way of talking about the shape of the orbit. This lambda out front here just has to do with that constant that was in the definition of y from u, that has to do with the angular momentum and the masses and the Newtonian's gravitational constant. This is called the radius of curvature. I think it's got some other Latin names that are going out of style, but really it's got the units of length, so it's sort of an overall spatial scale of the orbit. It's the sort of the magnification factor of the orbit. In general, how big is the orbit? And we'll talk about exactly what that means when we talk about the specific cases. And of course, there's still the theta naught, the other integration constant from the second order differential equation that tells us how is the orbit oriented with respect to theta. Yeah, I mean, it's not that optimal to write this eccentricity in terms of this y naught, because that has no sort of physical meaning. So one of the things that's often done, and I wrote this and I put this in smaller text here because it's not crucial to go through every step. If you take this solution, you put it into the definition of the total energy, which is a constant, and you solve for the eccentricity, it turns out that you can write the eccentricity in terms of the total energy, the angular momentum, and the masses of the particles, which is a more physically based way of writing that eccentricity. All right, we're coming to the end of this video. I just wanted to show you one more thing, just because if I mentioned conic sections, I can't not show you actual pictures of them. So these are the orbits that we're going to be talking about. We'll go through them one by one in the next video. We'll talk about this effective potential and how it relates to the energies of the orbits, and we will do that soon.